So good morning, everyone. How are you holding up? Okay, so some people kind of look at their feet and other people are like, yeah. Okay, so this marks the transition between the three introductory courses that you had and the courses that are intended to introduce you to some kind of current research areas. And of course, the research courses are trying to build on the introductory courses that you had. So first of all, I think we should say that you've had some really great introductory courses, don't you think? They're really good. Yeah, exactly. All right, so thanks to Dan and Ed and Bob for setting the rest of us up very nicely, I think. Okay, so this course is about relational parametricity. And you can see that it's a departure not only in terms of the intent, right, to try to tell you a little bit about a current research area, but also I'm the first person using slides. So I don't know if other people will be using them or not. But one problem with slides is that it tends to let one go very fast. So I'm going to try not to do that. Okay, so what I'm going to do is give these 4 lectures, and they're basically based on a paper about what's called bifibrational parametricity by me and a bunch of other people. So the overall topic is Reynolds' theory of parametric polymorphism, or parametricity for system F, and Bob talked a little bit about this in his lectures. And the goal is essentially to extract the fibrational essence of parametricity from Reynolds' original construction. So I won't say model, even though I did in the abstract for the course, but I should really say construction, because as Bob pointed out, and as I will mention, it wasn't quite right, but it was really close, and the ideas were really, really good, really right ideas. So we're going to try to extract the fibrational essence of Reynolds' theory, and then we're going to use that, the insights that we get from that, to generalize to very general models. So there are 4 lectures. The one we're going to have today will just tell you what Reynolds' theory of parametricity for system F is. So I know Bob talked about it a little bit, but I'll talk about it a little bit more. So that's today. Then after that, we'll have an introduction to fibrations, because if I'm going to try to extract a fibrational or bifibrational essence of parametricity from Reynolds' construction, then I probably ought to tell you what that means. Then we'll look at Reynolds' construction through a fibrational lens once we have that tool. That'll be in the 3rd lecture. And then finally, we'll use all of this machinery that we've built up in the 3 lectures to make a parametric model for system F. So that's the idea. That's the plan. Okay. So what about these parametric polymorphic functions? Well, you already know about them a little bit, because Bob talked about them, and actually Dan talked about them as well. Parametric polymorphism, it captures this idea of uniform behavior of functions across different type instantiations. Okay? So this is distinct from ad hoc polymorphism. So when I say ad hoc polymorphism, I can't remember if it was Dan or Bob was using a different term, but what I really mean is the kind of thing that you get like in Haskell type classes or something, where you could have a class that has a plus that means one thing, and you could have a different class that has a plus that means a different thing. So that's what I mean by ad hoc. And what we want to do is not have that. So we want to have this uniformity across types. So that means, in particular, that the functions have to be given by a single algorithm. I mean, I'm just speaking intuitively right now. But your function should be given by a single algorithm at all types. And in particular, it can't make use of any type-specific operations, or I could say values either, right? So I can't have something that's type-independent if it uses something that's type-specific. Okay, makes sense. Yeah, somebody's going, yeah, of course. Exactly. Okay, and remember that the idea with parametric polymorphism, or as I'll probably say just parametricity, is that you want to map related inputs to related outputs. So if you remember the example that Dan was doing about this representation independence example, right? So the idea there is you want to map related things to related things, and it shouldn't matter somehow what the internal representation is, right? So that's a kind of thing that parametricity can talk about. Okay, so this is parametricity not in general, but for system F. And I actually was not here on the first day, but I assume that somebody showed all the syntax for System F. Okay, I'm going to just remind you of what that is. Not because I think you've forgotten, but because it's probably good for me to indicate the notation I'm using, because it might differ. Okay? Okay, so in syntax, parametricity is kind of captured by this for all type constructor, right? So, you have a type like, for all x, x arrow x or something. And you have this intuitive idea about what this for all is meaning. So that for all type constructor is really trying to get at this idea of parametricity. Semantically, as I said, you want to map related inputs to related outputs, and you want that to be the case not just for arrow types, where it's pretty clear what that means, but in the complicated case, like for all types as well. And the relatedness requirement is going to capture this idea that we don't want to have ad hoc functions. And the way that I like to say this is that it means that for all really means for all, right? So just because you write down, just because you walk around and you write down this nice upside down A, and you say, I call that for all. That's the for all type constructor. Well, how do you know that it's really for all? How do you know that it behaves like for all? Right? That's what parametricity is about, saying that for all really means for all. Okay? Uh-oh, what's happened? But yes, magic is back. Okay. So all of this stuff comes out of Reynolds' paper called Types, Abstraction, and Parametric Polymorphism from 1983. And there are electronic copies around, as well as physical copies. It was an invited paper back then. And his idea was, okay, I'm going to construct a set theoretic model of parametric polymorphism for System F. And his idea was to do this compositionally. So I think some people have been calling that structurally. So in other words, you're going to do it by noticing that, for example, in System F, types are built up in this nice kind of compositional manner, like types are built up from smaller types, right, using type constructors. So the model's going to be built up in the same kind of way. Okay? So what he does is he gives a set interpretation for every type. So this is going to be a set model. So he's going to give an interpretation of every type in terms of sets, an interpretation of every type in terms of relations, and then a set interpretation of every term. So if I slice this differently, I can't do that now because I've got this on a slide, but I would have said a set interpretation for every type and a set interpretation for every term. So that's giving a set semantics, a set interpretation for all of System F. And then because I want to get at this notion of relatedness, a relational interpretation for every type. So I have to say what it means for two terms at a type to be related, or for their semantics to be related. Okay? So I could have sliced this slightly differently. Instead of saying, for types, I do set and relational, and for terms, I do set. I could have said I do a set interpretation for the entire calculus by giving a set interpretation for every type and a set interpretation for every term. Oh, and then I have to say what it means to be related at a given type. So I could have sliced it a little bit differently than I did here. But I've sliced it this way here because that's the way I'm going to talk about it when we start building up this model. Okay? So then, after Reynolds sets up all this machinery, he proves an abstraction theorem based on his construction. And this is the same abstraction theorem that Bob talked about. So in effect, what it says is every term is related to itself by the relational interpretation of its type. Okay, so that's a way to say it. But here's another way to say it. If the arguments to a function are related at the relational interpretations of their type, so remember every type has a relational interpretation associated with it. We're going to do this. We're going to drill down and do this in detail. Just trying to give you an idea of what's happening. Okay. So if I have a function and I feed it things that are related at the right type, then I should get results that are related at the return type of that function. That's the idea, okay? So that's, again, this idea of uniformity. And so Reynolds proves a theorem called the abstraction theorem, but he does it based on his machinery, which I don't quite want to say model, so his construction, makes a formal result out of it. Okay, but there's a little caveat here, which I keep alluding to and kind of stumbling over, which is that Reynolds discovered that his own construction was flawed, and Bob mentioned this already. So Reynolds discovered that his own construction was flawed. In other words, there aren't any set models. So he was trying to work in set, trying to build a model in set, but it turns out that you can't do that if you're working in a classical set theory. So if you have a classical meta theory, you can't do that. Okay. So I'm not going to go into the details of why you can't. I'll say a little bit, and I'll come back to this point right at the end of the lecture today. Okay? But I will tell you that the next year, Andy Pitts showed that set models do exist if you're working in a constructive set theory. So all is not lost. And even though Reynolds' construction didn't quite work as he originally set out, like I say, it was so much the right idea. So you can't really say, well, Reynolds failed, because he really didn't fail at all. There was just a subtlety, right? Okay. So subsequently, a number of models for parametric polymorphism for system F have been constructed. There's like a model based on partial equivalence relations and, lots of different models. And I'm going to tell you about a particular one, and it's based on bifibrations. And like I said, I'll tell you about bifibrations in the next lecture. And the reason I want to tell you about this model is because I think it has this nice property of hitting a sweet spot between simplicity on the one hand and being able to have properties that you want on the other hand. Okay, so there are other models, lots of other models. Some are more complex, some are less complex. Some not only model system F, but also some logic for reasoning in system F. But this model isn't going to do that. This model is just going to be a model of system F, and it's going to have simplicity of what we could call functorial models. So what I mean by this is that types, in functorial models, types are interpreted as functors, and terms are interpreted as natural transformations. And it's going to have that kind of property, not exactly that property, but very much that kind of property. And at the same time, there's enough structure there to derive sort of standard consequences of parametricity that are used as a gold standard or a litmus test for good models, right? So if you build a model, that's one thing, but you want to build a good model. And a good model means one where, for example, functors have initial algebra. Well, functors that should have initial algebras, so they can represent data types. Similarly, for final coalgebras, you can have like graphs of functions in your model, and so on. I think parametricity should imply dinaturality. So there are properties that good models are expected to have. Now, we won't have time in this course to talk about those, but they are in the paper that these lectures are based on. Okay. So this is maybe a good time to just pause and say something I should have said at the beginning, which is that there are some exercises for this course, and also there's the paper for this course. And I didn't put them on Piazza because I didn't know about that at the time. So they're on my website. So if you, I think there are links on the schedule page. I think there are links to the instructors' websites. If you go to my website, it'll say something pretty close to the top. It'll say materials for OPLSS are here. Okay. And if you go there, you'll see exercises for today, and you'll also see the paper that this is based on. So you have something, a compressed form, but really concrete that you can look at, and you have access to that. And about the exercises, there are only 2 for today, and they shouldn't be too difficult. But if you haven't done, for example, Ed's exercises, then you could use the time that you might have spent using my exercises, if there had been more, to complete his. And the reason I suggest this is because next time, so today there isn't going to be, I think, nothing that's categorical. I think there will be nothing that's categorical. But next time there will be, and the time after that there will be, and the time after that there will be. So I'm going to even, those of you who, if you just saw, products and exponentials for the first time yesterday, or products 2 days ago, exponentials yesterday, it might be a little bit hard to understand what I'm doing if you're not, completely comfortable with those things. So you could take a look, you could, use some of the time to, I don't know, bone up your category theory game, right, to become a little bit more comfortable so that the things I say at least have some pegs to, for you to hang ideas on. Okay, so just 2 little exercises today, but nothing categorical, just induction on types. Okay, so this is where we're going. We're just going to talk about System F, and we're just going to talk about Reynolds construction for it. Okay, so I did, as you all saw me confirm with Dan that he talked about the syntax, or someone talked about the syntax of System F. But I'm just going to take a moment to kind of remind you and also reset notation, because I might be using slightly different notation than previous lectures. So I'm going to, a type context is delta, is just a list of variables, right? A list of type variables. And then a type judgment just looks like delta proves tau, where tau is a type, which I'm going to tell you about in a minute, and delta is a type context. So the idea is that the free variables in the type are here, and then tau is the type that's constructed from those free type variables in the usual way. So hopefully this is familiar, but if we can go over them fairly quickly. So if I have a variable in a context, then that context proves that that variable is a legitimate type. I can make an arrow type if I can make the components of the type in the same context. And I can make a for all type if in a slightly larger context I can make the body of the for all type. Okay, so is that okay for everybody who's familiar with that? So I don't know what was used for the type context before? Delta? Yeah. Perfect. Okay. Yes, so many conventions. All right, and of course we consider alpha convertible types equivalent. Okay, so the standard thing. What about terms? Well, so let's talk about term contexts just a little bit. So a term context I'm going to call gamma, hopefully also consistent with before. So a term context is going to look like delta proves gamma. Delta is a type context. I've got a bunch of term variables, say maybe m of them. Gamma is going to be of the form, this term variable has this type, and I'm going to have a whole bunch of those. And then, of course, I'm assuming that my type context gives me that the types of the variables are actually well formed. Okay? So again, I think this is probably what you saw. And then once you have that, you can make a term judgment. So in a context, a type context gamma, a type context delta, a term context gamma, I can prove, or I can form the term T has type tau, provided I have sort of all of these sort of preconditions. So I have a type context, I have a term context, tau is well formed in the type context delta, T is a term, and I have to show you what the judgments look like. And again, these should be very familiar by now. But this is really just to try to set notation. So they're the same ones that you probably already saw, that if you have an x, a variable, term variable x of type tau, xi of type tau I in gamma, then you can prove that x has type tau, xi has type tau I. You can make, you can do type abstraction, right, with the usual typing rules. You have to expand the context when you're typing the body. You can do type application in the usual way. Again, you can do type abstraction in the usual way, where you again have to extend the context a little, but now you have to extend the type context. Here is just type application. So this should all be familiar, right? Okay, good. So I won't belabor it, but you have something that you can refer to so you can see the syntax I'm using. Usual caveats about alpha not appearing free in gamma here. Okay. And usual caveats about my substitutions being capture free. Okay. So just the standard setup, that's all. But I'm trying to model not just a bunch of terms, I'm trying to model an equational theory. So What theory is it? Well, it's the one you're thinking of. It's the one where alpha equivalent terms are considered equal. So by alpha equivalent, I mean like at the type level and at the term level, where beta equivalent terms are considered equal, where I have eta expansion both at the type and term level, where I have, if I have two bodies that are the same, I can abstract them and get things that are the same, again, at the type and the term level. Okay? So things you probably always have in mind, even if you didn't realize you had them in mind. And a couple more. If I have terms that are equal and terms that are equal, then if I apply the first terms to the second terms, then I get things that are equal, again, at the type level and at the term level, and that I have an equivalence relation. So my equality is equality, and it respects the structure of the calculus, the computational structure of the calculus. That's all I mean. Okay. So great. That's the syntax. So now how are we going to model all this stuff? So what Reynolds does is he defines two parallel semantics for system F. So what we're going to do is we're going to start and give us semantics of types, and then later on we'll give us semantics of terms. Later on today, we'll give us semantics of terms. But I'm going to start with the types, partly because the types logically precede the terms, and also because it's a little bit easier. Okay? So Reynolds gives two parallel semantics. So he gives what I would call an object semantic. So this little O right here is supposed to be for object, but for us, the objects are sets. So I could have put an S here if I wanted instead, but I didn't. I used O because that's what I'm going to generalize. When I generalize this, the O will be very handy. Okay. So I'm going to give an object or set semantics. So the idea here is that I've got a bunch of type variables in delta, and I want to make a type. So if you tell me how to interpret the things, the variables that are in delta, these free variables in the type, then I can tell you how to interpret the type. Okay? So I don't think any surprises, but still, it's good to spell out what we're doing. I told you that for types, we'd also give a relational semantics, and it's going to follow the same form. So R here is for relational. So I'm going to always have an object semantics and a relation semantics. And of course, for the relation semantics, I have to do the same thing, right? I have to say, well, if you want to interpret a type tau as a relation, then I suppose you better be able to interpret all the type variables as relations as well. And so that's what this semantics R is going to do. I haven't done it yet, but that's what it's going to do. So I'm going to introduce a little bit of notation. I have to be careful here because I don't want to say things like category today. So I'm going to write S:(S) if S is a set. I'm going to write R:(rel) if R is a relation on sets. So just a subset of a product, right? And I'm going to write R:(rel xy if R is a relation specifically on the sets X and Y. So in other words, if R is just a subset of X cross Y, what I just said. So R:(rel) if you have any relation, like here, just any old relations, but rel of xy if R is a relation on X and Y. Okay, so that'll just make some of the notation on the board, on the screen, not the board, a little bit easier. Okay, and I need a few more ingredients before I can do anything. So if I look up here at my object semantics and my relation semantics, the object semantics is expecting cardinality of delta many sets in order to give me a set interpretation of tau, right? And the relation semantics is expecting cardinality of delta many relations to give me a relational semantics of tau. So I'm going to have the convention that X bar is going to be a cardinality of delta tuple of sets. So it's going to be just the right number of sets to interpret delta. And similarly, over line R is going to be a cardinality of delta tuple of relations. Okay, and I'm going to adopt the convention that in here, this over line R, I've got a whole bunch of relations. I'll call them each one, the individual ones, for example, Ri, and I want Ri to be a relation on Xi, Yi. Okay. So we're going to see this on the next slide. why this is useful, but that's the idea. So Ri is over xi, yi. It'll just be easier to, kind of, if we just have that convention throughout, it'll be easier to remember. Okay. Finally, I'm going to need a specific relation. This is called the equality relation. And if you give me an element x in some set x, then the equality relation is just, well, it's just a diagonal, right? It's just the only things that are in the relation are pairs of something with itself. Okay. So everybody good with the conventions and ready to try to interpret some types? Okay, I hope so too. Okay, here we go. So I'm going to do this by kind of induction on the types, right? So I'm going to say I've got 3 different kinds of types. I've got type variables, right? I've got arrow types. I've got for all types. And what I'm going to do is tell you how to interpret each kind of type. And I'm going to do it by telling you how to interpret the components, except for the variables. I can't do that. Okay. So this is essentially constructing what we're essentially going to do here is construct a type index logical relation, but I'm not really going to talk about it in those terms today. But if you're trying to relate this back to some of the things that people were saying about logical relations, that's what we're doing. Okay, so here's what I'm going to do. For type variables, it's really straightforward, right? I just say, okay, I've got this context delta, and it proves that alpha I is a type. So that means that alpha I must have been in here, right? In order for this type to be well formed. So what am I going to do? If you give me a bunch of sets that interpret all the things in delta, I'm just going to project out the right one. Okay? Okay. And I'm going to do exactly the same thing for the relational semantics. Okay. So there are two, yeah?
Is the putting them next to each other like application or something like that?
Oh, yeah. So remember, let's go back. So this is supposed to be some kind of function, right? So I'm supposed to take cardinality of delta many arguments. So it's exactly application. Perfect. Okay. Yeah. So okay. So we gave the 2 interpretations for variables, and that was pretty easy, right? I'm not quite ready to go on to the arrow types yet, because I want to make a couple of observations here. So the first observation is that these things are these 2 semantics, the object semantics and the relation semantics, are completely independent of one another, right? I mean, I didn't have to know anything about the relation semantics to give the object semantics, and I didn't have to know anything about the object semantics to give the relation semantics. Completely independent. Okay, that seems trivial, but and it is here, but we'll come back to that. The second thing I want to notice I didn't put on a slide. Well, it's on the next slide, but let's write it here instead. So, whoops, let's not do that. Let's go back to the slide we want. So what I want to notice is that, remember I know it's hard to see no matter how big you write. So tell me if you can see in the back. So remember I said that relation Ri is going to be a relation on xi and yi? Remember that? So that means if you look at what happens with variables here, if I look at the relational interpretation of my variable alpha I, that's just Ri, right? And if Ri is over xi and yi, then let's have a look at this. Oh, this is the relational interpretation. If I look at this pair, just not going to stay. Okay, fine. If I look at this pair, then what you can see is that whenever Ri is a relation on xi and yi, this thing, remember, was xi, right? And this thing is yi. So what I have here at the variable level is that the relational interpretation of a variable is in the relation between the relational interpretation of that variable in the context created by all the domains of the relations here and the codomains of the relations. Okay, so we're going to come back to that, but that's an important property. Okay, so it might seem a little bit confusing because I've said there's no dependency between the relational interpretation of a type variable and the object relation, and that's true. I didn't have to know about the relational interpretation to define the object interpretation or vice versa, but they're still related. So there's no dependency, but there's a relationship. Is that okay? All right. Now I'm ready to talk about arrow types. So what happens for arrow types? Well, you already know what happens for arrow types. It's just the standard thing, right? Because if I want to give an object interpretation of an arrow type in some type context, I just interpret the thing to the left of the arrow in the same type context and the thing to the right of the arrow in the same type context. But now this arrow is a type theoretic arrow, and this arrow is function space between sets, right? So this is a syntactic arrow, and that's a semantic arrow. Okay, so no surprise there. And maybe a little bit of a surprise here. Okay, so how do I give a relational interpretation of an arrow type? Well, you somehow want to say, you'd like to say the same thing here, but just put like R's instead of all these zeros. And that's effectively what I've written here. So what I do is I say, well, when are two things of arrow type related in the relational interpretation R bar? Well, what do I do, or the relational context R bar? I say, if you give me two things that are related in the relational interpretation of the thing on the left, I get two things that are related in the relational interpretation of the thing on the right. Okay? So remember the idea with parametricity is that you want to map related things to related things? So what I've done is I've just set it up so that I map related things to related things. So, okay. So that's good? Okay, so let's just stop and make our think about these two observations. Remember, after we defined type variables, we made a couple of observations. I noticed that there's no dependency in the definitions here. And then we had a look at where the pair of the object interpretations lives. Yeah?
So it's all the functions, F and G, that preserve the relation, right?
Well, kind of. So it's all the functions of the right types that preserve the relations. So yes, that's exactly what I was going to get to here, right? Because I didn't say anything about where these F and G's live. Okay, but where they live, well, the F lives in the relational interpretation of the type, in the object interpretation of the type in the context that's made from all the domains, and the G lives in the object interpretation of the type that's made from all the codomains, in the context that's made from all the codomains. And so I have this same property, but I have it by construction. So at the variable level, I have it just because my relations are over their domains and codomains. But here, I insist that I still have it as I go up to the variable types. Okay, so now, so that was one thing to observe. And the other thing to observe here is that I can define the object interpretation without any reference at all to the relational interpretation, right? There's nothing about brackets R here. Okay. But notice that if I try to define the relational interpretation of a type, it does depend on the object interpretation. Okay. So I don't have that nice independence I had before. I've got a little bit of dependency, but not too bad. Okay. Just enough to make sure that that relational interpretations, or maybe put it this way, that pairs of object interpretations in domain contexts and codomain contexts are related in the relational interpretations of the relations that have those domains and codomains. Okay. Now things start getting a little bit crazy. Because now I want to talk about for all types. So just to go back, I think this is basically what you'd expect, right? I want functions to map related things to related things, so I just kind of write down the obvious thing about what that means. Okay. what about for all types? Well, things start getting a little bit crazier because for the object interpretation, well, so this is the part where I have to wave my hands a bit. This is the part that kind of didn't work in Reynolds construction. So I'm just going to say some things, and they might be kind of vague. But it's reasonable to think that, that this object interpretation of a for all type should somehow be the collection of functions that, well, that somehow for every set, so I'm working in semantics here, so I can't say for every type. So, but for everything that could interpret a type, right? This is like what Bob was talking about with his candidates of reducibility, right? So everything that could interpret a type, every set, I want to sort of look at the body, which has one more free variable, and I want to give an interpretation for that, and somehow I want to take the product of all of those. So I want F to be something that takes a product of all of those things. And I actually mean product in the sense that Ed meant product when he was, talking about products and categories, but now I've kind of got this infinite product. Okay, so, oh yeah, but I said I wouldn't say category, so sorry. Just a little heads up. Okay, so I want to take all these Fs that can interpret, I want to take all these Fs that somehow are in the interpretation of the body of the for all type when the environment's extended with the new interpretation for the alpha. Okay. But I don't just want all of those. Just like here, I didn't want just any old F and Gs. I wanted the ones that make related things go to related things. So I want the same kind of thing here. So I want to somehow map related types to related types, right? So what does it mean for two types to be related? Well, the only reasonable thing, I think, is that there's a relation between them. So suppose I've got a couple of things that can interpret types, so a couple of sets, and I've got a relation between them. Then if I take this function that I want to be in my interpretation of a for all type, and I apply it to the domain of the relation and to the codomain of the relation, well, I want to get things that are related. But I have to unpack a little bit here. So what does it mean to apply F to X prime or F to Y prime? What I mean is I've got this product, so I just want to project out the appropriate thing in the product. So I'm basically letting this S be X prime here. So I'm looking at the body of the type in a context that not only has the original stuff, right, this X bar, but where this S is now my X prime. And then I'm doing exactly the same thing here. Okay. And I want those to be related in the relational interpretation of the body. Right now I've got two things that are somehow, I've got two object interpretations of the body of my for all type, and so I want those to be related in the relational interpretation of the body, but this is going to take a whole bunch of relational interpretations of the things, not only in delta, but also of alpha. Well, for alpha, it's easy, right? Because I chose this R prime to be the interpretation, the relational interpretation for alpha, so I'm just going to use it. But I want to hold everything else constant. So that's what this equality relation is going to do. So remember this was on 2 slides ago, and that's the relation that just consists of all the pairs of things in themselves, right? So essentially what I'm saying is I'm going to hold all the other interpretations of all the other variables constant, let them be whatever they are, and according to the context. And then for this alpha, I'm going to use R prime. Okay, so there's a lot of detail here, and again, it all doesn't quite work out, but we're just trying to draw inspiration from Reynolds' ideas here. So if you're getting the idea, that's good enough. Okay, so I want to take related types to I want to take related things to related things. Just like here, I took related things to related things. That's the idea. What about the relational interpretation? Well, you might think it'll be worse, but if you suffered through all of that I just said, then it shouldn't be too bad. Because what do I want? I want the relational interpretation to be, well, when should two things be related at a for all type? Well, I should have two functions that for any thing that could be a type that has a domain, so for any relation, has a domain X prime and a codomain Y prime, just like above. when I apply f to the x prime, and not f to the y prime, but now g to the y prime, because I'm talking about two different functions, I want them, the results to be related. So here I'm still using r prime in for alpha, where alpha is my bound variable here. But I have to consider all relational interpretations of the type variables in delta as well. So up here I fixed them. I fixed the interpretations of the other type variables, but here I'm letting them range over the things that are in the argument, right, in the context here. Okay. So I've got a bunch of interpretations, and because you might ask, where do the F and G live? Well, they live in the object interpretation of, so F lives in the object interpretation of the type at the domains of my relations, and G lives in the object interpretations of my for all type in the codomains. Okay. So, all right, so that was a bunch of stuff, but the idea is that you try to build up these interpretations in such a way that you map related things to related things. That's what we're all about here, and it kind of looks like we've done it. Okay, so that's what oh, sorry, yeah. Thank you. Yeah, well, see, that's why I said it kind of looks like we've done it. So I've tried to hint that Reynolds construction doesn't quite work, okay? And I will come back to that at the end. But that is one problem, yes, definitely. Yeah, absolutely. It's not the only thing, but it is one thing, and it's a key thing. Okay. Okay, so we've constructed things, or at least it looks like we've constructed things so that related inputs go to related outputs. This is the property that I drew up on the board in the case of variables, and then we kind of talked about for the other types. So if I have a bunch of relations over a bunch of domains and a bunch of codomains, then the interpretation of a type with respect, the object interpretation of a type with respect to the domains, paired with the object interpretation of the type with respect to the codomains, is in the relational interpretation of the type with respect to the relations that have those domains and codomains. So that's this property, which is nice. And what we should notice is that the interpretations get progressively more intertwined. So remember here, no dependency. Here, the relational interpretation depends on the object interpretation, but not vice versa. Check this out. The object interpretation depends on the relational interpretation of the body. The relational interpretation depends on the object interpretations, but okay, we saw that here, so we're not alarmed by that. But you've got this kind of weird interdependence going on, right? I think that's a little bit unexpected. But if you try to say what it means for a for all type to map related things to related things, you're just led naturally to this kind of interdependence. Yeah?
I don't get the motivation why you have to do it this way.
Do you have another way? Do you have another way?
Yes, you can say that for the object relation, you can say for any predicate, not for any relation. For any predicate, just explore that predicate.
But a relation is a binary predicate, right? So I wanted
a unary predicate. So
a relation.
Then you don't get this.
Yeah, but then how do I talk about two things being related, two things that aren't the same being related?
But that's the other relation, the relational interpretation. Yeah?
Well, that's what I'm giving.
Okay.
I think I'm.
Okay.
I mean, I am giving. I don't know how to do this without giving a relational interpretation. Okay. Okay. Well, we can talk about it afterwards, so I can try and maybe understand better. Yeah. Was there another question? Okay. All right. So things are getting progressively intertwined. Object and relational interpretations of type variables, independent. Object interpretation of an arrow type doesn't depend on the relational interpretation of the relational interpretation, but the other way around. And the object and relational interpretations of for all types are just really interdependent. So we don't have to have two, we don't really have two semantics, right? So I said that Reynolds kind of sets up two parallel semantics, but we really have one semantic, so kind of interconnected semantics. So it's a little bit more complicated than it appears at first. All right. So before we talk about the interpretations of terms, let's talk about the identity extension lemma. So Bob mentioned this. This is important for many applications of parametricity. And if you notice what we did, we made, like I said, we made up these interpretations in this kind of structural way, where you could imagine if you have a complicated type and you want to understand its interpretations, you would just kind of peel apart the structure, right? Okay, so what that means is that if you think about what happens when you interpret a type in a context that interprets all the type variables as equality relations, then you could ask, do I get an equality relation? And the identity extension lemma says exactly that you do. So the way that you state it is, if you have a type and you interpret that type in an environment where you interpret all the type variables as equality relations, then you end up with the equality relation on the interpretations of the types in the context on which the equality relations are formed. Okay, and it's exactly the same identity extension lemma that Bob talked about. Okay, so that's types. What about terms? So terms are a little bit more complicated. So the first thing we have to do is talk about interpreting these term contexts. So if I have a term context gamma, it looks like a bunch of type variables with associated types. And I'm just going to interpret those as products of the interpretations of each of the component types. Okay, so this is product. These are products of sets. And similarly, for at the relational level, I'm going to do exactly the same thing. Okay, so I've got these contexts. I just think of them as products. And an object interpretation of a term is going to be a family of functions. It's going to be parameterized over a set environment, right? Because I should feed in a bunch of sets to interpret the things in delta. Okay. So for every such set environment, I'm going to interpret a term as mapping interpretations of types to interpretations of types. So it's going to map the interpretation of gamma in the same environment to the interpretation of this tau in the same environment. Okay, again, should be completely standard. And then, so I'm going to define these, and I'm going to hopefully try and sanity check the definitions with you as we go along. Okay, we'll see how sane you stay. All right, variables. Variables are always easy, so let's have a look at those. So suppose I have this type judgment, this term judgment. Then I need to say what the interpretation is. So I'm going to say this. Remember, I'm trying to give, for every x, I'm trying to give an interpretation of a set interpretation of the variable with respect to this context, the things that are interpreting this context. Okay, but I have to feed it some arguments because such a thing should be a map from the interpretation of gamma to the interpretation of the term I'm trying to interpret. So if I give a bunch of A's, so an A bar, a bunch of A's that interpret the context, the term context now, the X's are interpreting the type context, the A's are interpreting the term context, then I hope I get something over here, right? And I've made the definition that this interpretation is going to be AI, and that does make sense because if AI bar is a bunch of interpretations of the context in X bar, then AI does exactly have the right type. So I've made a definition, and at least I have something that type checks. Okay, so that's good. That's my sanity check. That's what I was going to offer you as my sanity check. And there we have it for variables. So I just project out, if I have a term context and I have a variable, I just project out the corresponding interpretation. That's all, just like we did it for the types. What about term abstractions? Well, again, this isn't so bad. So I have to tell you what's going on, how to interpret the thing below the bar based on how I interpret the thing above the bar, right? Because this is just a big induction on the structure of the derivation. Okay, so I claim this, but let's see that it's sensible. Okay, so I want the interpretation of a type abstraction, or sorry, of a term abstraction, to be a map from the context to the term. Well, the interpretation of the context to the interpretation of the term, but in the same type context. And so that's what I've written here. And then I just remember how I interpret arrow types. I interpret them as, well, function space, right? Functions between sets. Okay, but by the induction hypothesis, right, about the stuff above the line, I know that its interpretation says, well, if you give me an interpretation of its context, but now I've got an extra thing in the context. So I've got, in the context, I have this interpretation of gamma, but I also have an extra interpretation of tau 1, right? Because we're interpreting the context as just products, so there's my product. Then I should get something in the interpretation of tau 2. Oh, well, that looks pretty good, because if I were to come up here and take this thing, that's this, with respect to x, and feed it a bunch of a's, and feed it another a, then I do get something that at least lives in the right place. Okay? So I claim that that's a reasonable definition. What about type applications? Well, it's the same game. So again, I need to interpret the stuff below the line based on the interpretations of the stuff above the line, and I'm going to just offer you an interpretation. And I'll argue that it's reasonable because, well, what happens? What I want is that the interpretation of the stuff on the left-hand side maps from the context to the return type. What does the induction hypothesis give? Well, it gives, if I look at this piece, it gives that its interpretation maps from its context to its return type, right? But remember that, again, this is an arrow type, and the interpretation of arrow type, you just split it up into a function space. What about the other hypothesis? Well, the other hypothesis, again, will say that if I want to interpret the term T1, I have to go from its context to its return type. And now I've got, if I look up at the term I formed, I've said, well, if I look at this thing, and I apply it to a bunch of A's, then if I were to give it something of this type, I would get something of this type. But I've got something of this type right here. What is it? It's this thing applied to exactly the same A's. And that's exactly what I wrote right there. Okay. So far, so good. Everything looks pretty good. We're all going along, but we haven't gotten to the hard part yet. Okay? Because we haven't talked about how to interpret terms of for all type. But so far, everything looks good. Everything's in the required sets. Hopefully my sanity checks have convinced you that my definitions are at least reasonable, even if they're not the first thing that you would want. But what Reynolds found is when he interpreted type abstractions and type applications, that the terms are in the required sets, he ran into problems. So let's have a quick look at what problems he ran into. I won't go into them in great detail, but I think you can get a little bit of a flavor. So let's just see what happened when he tried to interpret like terms of for all type. So it's reasonable to think that you might use some kind of product to interpret the for all types. Okay, that's a reasonable first pass. I'm going to, it's already been the issue about whether or not that's truly reasonable has already been raised, and I will come back to that in a minute. But if you'll just bear with me for a moment and say, okay, well, you know, for a first pass, maybe it makes some sense. Then I might try to make this kind of a definition. I might try to say, if you want to interpret the stuff below the line, interpret the stuff above the line, but oh yeah, I've got this kind of extra type variable here, so I'll just make a product that ranges over all the things that could interpret that type variable. Okay, just sort of what we did at the type level. Okay, so my sanity check argument would say, well, you know, it's not entirely unreasonable because, you know, if I want to interpret this term of for all type, then I should have something that goes from the interpretation of the context to the interpretation of the for all type. And then I might remember how I interpreted for all types, right? It was just a bunch of F's and some big products such that some thingies held. Okay, I won't elaborate the thingies because they're not important right now. So, okay. And if I were to look at the stuff above the line, what does the induction hypothesis tell me? It says if I try to interpret, well, what I noticed is that if I try to interpret the body of my term in a context, it has to be a little bit bigger, right? Because I've got this alpha here now, not just the delta, but I've also got the alpha. Then I should get if I try to interpret this term, I should get something that goes from its context to its return type. But here, remember the alpha can't appear in gamma, so somehow this alpha is free. So this interpretation, I never am going to use this S. So I can simplify that piece, which is good. And what's going on over here? Ooh, I don't know. I don't think I can do anything with that. Right? I just have to leave it like that for the moment. Okay. But if one of these for one S, when I apply it, has this kind of type, then if I were to first of all feed this thing a bunch of arguments, A, I'd get something over here. And if I took the product, right, then I'd have something that has a type that's this product, and that is at least the right kind of thing. So it's not, again, it's not entirely unreasonable, but I still have to show that all these conditions hold. Okay. So I'd have to check that. That's where the rub is going to come, part of the rub. Okay. So let's just leave this for a moment, and remember that there's a little bit of an issue here. I'm going to have the same kind of thing that happens with the type applications. Again, I'll just try to interpret the stuff below the line based on the interpretations of the stuff above the line. So I want the interpretation of the stuff below the line to map its context to its return type. So if I feed a bunch of contexts, I should get something in the return type. So I make this definition here. Let's see why it's reasonable. Well, here's the stuff I'm interested in. Here's its context being interpreted. Here's its return type being interpreted. So that's okay. The stuff, what do I know from the induction hypothesis? Well, I know that this term of for all type also maps its context to its return type. Well, the interpretation to the interpretation. And again, if I remember what the interpretation of for all type is, it's a bunch of these F's in this big giant product, such that some stuff holds. So if I start unpacking the thing I wrote on the right-hand side and apply this piece, which is this piece, to a bunch of A's here, I at least get stuff that's in here. But I have to do a bit more checking because now I need some kind of substitution lemma or something to make sure that I get things that are in this kind of substituted type. So there's a bit more work. So when it comes to the type abstraction and type application, I've got much more work to do. Okay, so I'm not going to go into the details of that, not because it's not interesting, but it assumes that the interpretation of type abstractions is sensible, and we haven't established that because we can't. All right, so what's the deal with the type abstractions and the type applications, right? That's whoever was asking that. That's what you were asking. Like, so what's the deal? Okay, so you can't, as you noticed, you can't interpret a for all type as just an unbridled product, right? Because here I'm saying I want to look at a product of all the things that can interpret types, including, the thing that's interpreting my current type. So that's a bit of an issue, right? That's the thing you noticed, and that is absolutely true. That is a problem, okay? So can't do that. So what Reynolds thought is, well, maybe I could cut down that product somehow, right? I mean, maybe I could impose some, well, he called parametricity conditions, so that I can cut down that space so that it's small enough to be a set, for example. I mean, I don't even know if this big old product's a set. Okay, so, but I can't just do that in any old way. I can't just say product means whatever I decide it means today. I want a product to mean something principled, like what Ed suggested product should mean, right? So we want products to mean like real products, and when you restrict to a binary case, you want real, like the thing you know is a binary product, or when you restrict to a ternary case, you want the thing you know as a ternary product. So we want to preserve binary products because we need those for interpreting contexts, right? We also want to preserve function space because that's how we interpret arrow types. So somehow you want to have like a weaker notion of a large product, right? So this big giant product. You maybe want to have some kind of notion of a large product that still coincides with binary products in the binary case, and it interacts nicely, I'll say, with function space, like normal function space. So that's the thing that you're really trying to have, because that's the way you're going to exclude these ad hoc functions. So, like I said, Reynolds thought about like how could you do this? How could you impose some property that will achieve this? He called these properties parametricity properties, and it leads to the kinds of interpretations that we've seen. Okay. But and based on these definitions, he proved his abstraction theorem. So he tried to give a sensible model and tried to prove an abstraction theorem. Did prove an abstraction theorem. But the model wasn't quite right. So that's why I try to kind of talk about his construction rather than his model. So the year after the paper I mentioned at the start came out in 1983, in 1984, Reynolds himself discovered that there was a problem with his construction. Okay, so if you interpret times as time, so product as product, arrow as function space, and for all as some kind of possibly restricted large product, right? That was his idea. If you do that, you can't make a set model of system F. So he showed that himself. And it's even a little bit worse than that, because it doesn't matter what notion of parametric you use. So it's not like he said, okay, let me pick this particular notion of parametric, and then, oh, it turns out I can't do that. Right, because then you could say, well, maybe that wasn't a good notion of parametric. Maybe you should come back and think about, maybe you should think about what parametricity should really mean, as if he hadn't already been doing that. But he showed himself that no matter what notion he chose, you couldn't make a set model. But he was working in classical set theory, and that's the issue. Okay, let me pause there for a moment, yeah?
Can you explain what you mean by ad hoc functions?
Yeah, so I think I did that right at the beginning, but I can say it again. So the idea is that like if you're programming in Haskell with like Haskell type classes, right, you could have like a notion of plus or a notion of times or something that means one thing in one type class and another thing in another type class, right? Okay, so somebody else used a different term. Did you use a different term, Dan? Or intentional, yeah, okay. So I just mean that. So I mean non-uniform, right? Because the whole idea with parametricity is that for all is supposed to somehow be for all, and it's supposed to be type independent. And so by ad hoc, I mean like not that. No, that's not what causes the size problems. Classical set theory causes the size problems. Or it doesn't really cause them, but it reflects them maybe. Say that again?
So I guess Reynolds thought that was the source of the problem that we ran into initially, and later proved that actually no.
Well, the product, so if you just try to take an unbridled product, it's too big. First of all, you don't even know if it's a set, and you're trying to make a set model. So I don't know, right? I don't even have a set. So that's one thing. So you might think, well, it's too big to be a set. So if I impose some condition, like a parametricity condition, then I might be able to make this product a little bit smaller, small enough, in fact, that I'd have a set. And so that's the kind of thinking. But it turns out it doesn't work if you're working in a classical meta theory. Okay? So it wasn't him, but also so that was 84. So the first parametricity paper was 83. In 84 is when Reynolds discovered that there's no notion of parametric that gives you a set model. So that is the parametricity, or polymorphism is not set theoretic paper. And in the same year, Andy Pitts showed that if you work in a constructive meta logic, then you can have a set model. Okay? All right. So I'm not going to look at constructive models of System F in this course, but I just wanted to alert you that there's an issue. What we're going to do is draw inspiration from Reynolds' ideas, because even though the construction didn't quite work out exactly the way he intended, like I said, it was very much the right idea. Okay, yeah?
I think related to his question, what is the problem with ad hoc functions then? That was unclear to me.
Oh, the problem is just that they're not uniform. So this is a theory of uniformity. It's a theory of representation independence, right? It's, I mean, it's an idea of related things going to related things. And if I have ad hoc polymorphism, then I don't necessarily have related things going to related things, because the idea is that, of course, you want to have the same algorithm at every type, right? And ad hoc is exactly the opposite of that. Yeah, it's like, oh, in this type class, I'll just define it that way. Oh, in this type class, I'll define it that way. Yeah, so that's the idea. Okay, so like I said, we're just going to draw inspiration from Reynolds. Yes, another question?
Can you hint as to why this model is going to be better than the constructor set model?
Well, first of all, it will be okay. So better is always a relative thing. So what I said in the beginning is that what I like about this model is that it hits a sweet spot between having all the passing the litmus test properties for being a good model, and it's not as heavy as some other models. So some of the models that you can construct get pretty heavy. I mean, of course, by the end of this course, you might think this one's heavy too, but I think it's a bit lighter than some other ones, and it gives me a chance to exercise your category theory, which is the real nefarious idea. No, I'm kidding. Okay, so let me finish up. I've got a few more minutes. I think I've got about 10 minutes. So let me finish up by just talking about the abstraction theorem. It's only one slide, so you've almost made it. So this is the same abstraction theorem that Bob talked about, and the same abstraction theorem that Dan used. So it formalizes the idea of parametric polymorphism. Intuitively, it says the interpretation of every term is related to itself by the relational interpretation of its type. So that sounds a lot like reflexivity, right? If you think about those candidates of reducibility that Bob was talking about, and how he was saying that it's not obvious that things are, relations are reflexive. This is basically a statement about reflexivity. So here's what it says. Okay. So give me some types, some interpretations of types, right, some sets, that are related in the sense that there's a relation between them, right? So I've got relations pairwise between these types. And give me some things that at least could be related by the relational interpretation of these types. Then if you give me a term that goes from some context, in some context, and it has some type tau, and if those things that could be related actually are related, then if I take that term and I apply it to types that are related in the sense that there's a relation between them, and to terms that are pairwise related in the sense that we've assumed, then what I will end up with is two things that are in the relational interpretation of the return type here. So this is why I say, if you say a term is related to itself, or the interpretation of a term is related to itself by the relational interpretation of its type. That's intuitively the way to say it. But what I'm saying is, if I take the interpretation of this term and I apply it to things that are related at the type level and things that are related at the term level, I should get related results. And that's exactly what we've said here. Okay. All right. So now I have to have the caveat. It doesn't make complete sense because we didn't finish our interpretations, right? We didn't have all of our spinach. Okay. But a model of system F in which this abstraction theorem holds and the identity extension holds is what Reynolds was aiming for. So that was the goal. That was the idea. Okay. So that's it for the technical content today. To give you kind of a roadmap of where we're going to go. Next time I'll introduce the idea of fibration or bifibration, both of them actually. We'll be able to see Reynolds construction and results through the lens of bifibrations. That'll be in the third lecture. And then in the fourth lecture, we'll actually generalize these constructions here in a bifibrational setting. So if you don't know what a fibration is, that's okay, except, so hopefully you will after next time. But you kind of do, because They were Ed's sorting hats. Kind of. So they're sort of like extra magical sorting hats because they have to have some other properties that Ed didn't mention because he didn't need them in his context. Okay, so you have seen a little bit, but I'm going to tell you some more next time. All right, so since we're generalizing, of course, Reynolds construction is an instance of this model. And here are the references. These are the papers I was talking about. This is Reynolds' original paper where he tried to make this construction. This is the paper where he showed that he couldn't. And this is the paper that showed that if you work constructively, you can.